Welcome guys to lecture 2 of the database 2 course. This is Dr. Wael Abu Saadat. I hope you're doing well, you're keeping your social distance, staying safe at home, and wearing masks whenever you go outside. So let's start the content of today. We are still here, by the way. I like to show you this chart of the database engine architecture so that we are reminded where are we. We're still at the bottom here where it says data files. We're still discussing how data is stored and the indices that are available to query and manipulate the data on disk. What we will look at today is B+3s. This is the most popular indexing data structure available in almost all SQL databases, and you will see why as we keep talking about it throughout this course. So let's first understand what is a B+3. So the first thing we're going to learn about B+3s is that it's a tree. Okay, so what does that mean? Well, remember binary search trees from the data structures course. If you have been doing ASM problems, you have seen other kinds of trees, like perhaps tries. So it is actually a tree. What that means is it's a data structure that is modeled as a tree. There is the root node at the top. You always start from the root going downward while traversing the tree. The second thing you will learn about this data structure is that this is actually a secondary storage data structure, which means it is a data structure made to be partially stored on disk and partially in memory. Now, this is something new to you. You haven't seen anything like this before. I mean by that, if you recall the data structures you have learned in the third course in your curriculum, you've learned stacks and queues and linked lists and priority queues and binary search trees and hash tables. All of these are actually in-memory data structures. They are created in memory, they are manipulated and accessed in memory, and there was no notion of saving the content to disk. It is possible to save the content to disk of a stack or a queue or even a binary search tree, but that was not discussed because it's really a feature of those data structures that they must exist in memory so that you can work on them. All of it must exist in memory. While what we are looking at here in the case of the B+3, parts of it could be on disk and other parts could be in memory, and you will still be able to work with it. And for that end, we're going to call it a secondary storage data structure. So generally, you could think of data structures as classified to in-memory data structures versus external storage data structures, or secondary storage data structures. Secondary storage data structure does not mean that they will reside permanently on disk and you cannot access them except on disk. Obviously, to access them, according to the von Neumann architecture, the von Neumann way of thinking, you have to bring them from disk to memory to be able to manipulate them. But the point is, in the case of in-memory data structure, you bring the whole thing in memory to be able to manipulate it. While in the case of secondary storage data structures, you can bring part of it from disk to memory to work on it and keep the other part on disk. Now, why this distinction? Why would we even need to have a data structure where parts of it is on memory and another part of it or the rest is on disk? Because in the case of databases, again, what we are always trying to support is huge data size. We are thinking of a table that perhaps is in hundreds of megabytes or hundreds of millions of rows, and consequently an index that you can create on this table or a column in this table will also be quite huge in size. Perhaps it's too big to fit even in memory. So this notion that we have a data structure that is partly on disk and only part of it exists in memory, and it's still usable in the sense that we could work with it, is actually a very nice feature of secondary storage data structures. Now, the third thing to learn about B+3s is that they are a special kind of a tree that is self-balancing all the time. What does that mean? Now, remember from your binary search tree lecture many years back, I hope you can remember that the problem with binary search trees is that they can get skewed. What do I mean by skewed? I mean that most of the nodes in the tree will reside on one side and the other side will almost be empty. And when a binary search tree gets skewed, just like the figure you have here, when a binary search tree gets skewed, you're not getting log n anymore. You are getting O of n access. Now this is a big problem with binary search trees. The idea is beautiful. If the tree is balanced, or even semi-balanced, you get log n. But you have no control on the data that you insert in the binary search tree. So if you get like the sequence we're looking at here, where there is an increasing set of numbers being inserted into the binary search tree one after the other, you end up with a skewed binary search tree, which turns to be like just a linked list, and consequently it's O of n, it's not log n. So self-balanced data structures or self-balancing data structures are trying to fix this problem, and they fix it by doing, as we will see, what we can describe as rotations, or basically manipulations, or if you'd like to get really an insight into this, it will be additional steps beside the basic steps supported, or the basic operations supported by the data structure. So while you say just insert or delete or update, it will do the insert or the delete and the update, and then it will do something else as well, which is to fix itself. And as long as it fixes itself with every step, every time you call it, you call one of these operations that's supported by the data structure, it's always balanced, because there's no chance of actually going unbalanced. So B+ trees have this very important feature, which is that they are self-balancing trees. They will always fix themselves, so that you always get log n, and you really need to do log n here. Okay, if you're talking about an index built on a table that has 600 or 700 million rows, you don't want to get the tree to get skewed, because your O of n here is going to be horror. Okay, it's going to be like really bad performance. Okay, it's like traversing a linked list of 600 million nodes. So you really need to get the log n here, and we achieve that through the way the B+ tree works, which we're going to describe soon. The next thing we need to understand about B+ tree is the rules or the invariants it comes with. So the first thing is all leaves at the same lowest level. This is what I was just explaining in the previous slide, that B+ trees are self-balancing trees. They are always balanced. Since they are always self-balancing, then they are always balanced, and what that means that all leaves will be at the same lowest level. The second rule is that pointers in the leaves will point to actually the table or the rows in the table that we are building an index for. Okay, so these two rules, the first one is related to balancing. This is a rule, which means it always has to be the case, and we will see how B+ trees achieves this rule, that all the leaves are at the lowest level and it's the same lowest level. The second one is related to how can we actually use the B+ tree as an indexing data structure. Because when we are actually traversing an index, our goal is to find out where is the row that we are supposed to include in our result set. And the information about where is the row is stored at the leaf level. So we'll always start from the root, going downward to the leaf level to get a reference, or to find out where is the row, to get a reference to the row. And that reference will typically be the page identifier on disk and the row inside that page. So here is a sample leaf node in a B+ tree. Remember from your early tree education, a leaf is the node that exists at the bottom of the tree that does not have children. So this is how the leaf will look like. It will consist of a number of values, and each value has an associated reference, which is basically where is that row, which page, and which row in the page. Okay, now what are these values? 52, 53, 54. I initially got them from the column I am building the index on. So these values must appear in the column. So the reference below the number 52 is actually telling me in which page of the table that row whose column value I'm building an index on is 52. And 53 has also a row, an arrow below it, and it's going to tell me which page of the table has this row where the entry I'm building the index on is 53. So the number 53 will appear in the field I'm building the index on. Okay? So let's say, for example, I am building the index on H, on the H column. So I retrieved the H column and I found these ages. So I had someone whose age is 52, someone else whose age is 53, someone else whose age is 54. And associated with every one of those ages is, where is that row? Again, remember we said that the table is going to be paged, and those pages will be stored on disk until needed, because we can't put all the pages of the table in memory at the same time. So if I got a query select start from where age equal to 52, I will, as we will see, start from the root going downward all the way till this node or this leaf node, and I will find the entry 52. And then I follow the reference to find out where is that row. That will give me the page address and the row within that page. So I go and load that page and add the row to my result set. Now, what is also included in this chart is a reference to the next leaf, the neighbor leaf in the tree. And this is something you have not seen before if you just studied binary search trees and no other type of tree. So this will enable you to traverse horizontally all the leaves from left to right. And as we will see, this will play an important role with us in how the B+3 works, or how we use the B+3 to answer certain types of queries. So again, this is a sample leaf node. I'm showing it to you in terms of the B+3 in bits and pieces, and then I will put the whole thing together at the end. This is a sample non-leaf. Now, in the non-leaf, I will also have a number of values, and there are arrows that guides me in the traversal starting from the root, in the insertion, deletion, and update, as well as in the search to where to go in the tree. The arrow to the left of the value will always take you to values that are less than that value, and the arrow that is to the right of a value will always take you to values that are greater to that value, greater than that value, or equal to it. And that's bounded by the next value in the node, if there is one. So let me explain what I'm saying here. The arrow to the left of 57 will take you to all the keys less than 57. The arrow between 57 and 81 will take you to all the values, all the keys between or equal to 57 and less than 81. The arrow between 81 and 95 will take you to another child node that will hold all the values that are equal to 81 or greater than 81 and less than 95. The arrow to the right of 95 will take you to a child node that has or holds values that are equal to 95 or greater than 95. Now notice that this is similar to a binary search tree, except this is not binary. You see, the word binary search tree the word binary in binary search trees is referring to the fact, or to the invariant, that in a binary search tree you could have at most 2 children to any node. In the case of the B+ tree, this is a general tree, it's not a binary tree. You could have as many children as you could, bounded by the number of keys stored in the node. So from the illustration here, it should be clear that I will always have n keys, some n. N could be 2, could be 3, could be 4, could be 5. And I will have n plus 1 references, or n plus 1 references to children of this node. As you see here, if I have 3 keys, 57, 81, and 95, then I'm going to have 4 references. Less than 57, between 57 and 81, between 81 and 95, and greater than 95. Okay? So this is a general rule, and it's a kind of common sense rule from how this is structured and how these references are trying to isolate ranges of values that we could traverse to or go down to and ignore the rest. Why are we splitting it that way? So that ultimately we get the log n. Because if you are actually getting a query select star from where value equal to 85, then coming to this node, you're going to ignore the leftmost reference, the second one to the left, and then you will follow the reference between 81 and 95. You're also not going to follow the reference after 95. So you're going to follow one of the 4 references downward to the node that has keys that are between 81 and 95, including 81. And that means you've ignored the other ones. You've ignored the other children. So if you keep ignoring like 3 quarters and working with the rest quarter, going downward in the tree, you ultimately get the log n. And that's why we are designing it that way, or that's why it was designed that way. Here is a full example of a B+3. Again, this is a tree, so we have a root node at the top. And now the bits and pieces, I hope, are falling in place. You are going to work with this B+3 just like you have worked with binary search trees, in the sense that you make a decision as you start from the root going downward where to go. So if your query selects star from where value is equal to 70, so 70 is less than 100, you follow the left reference, and by doing that you've ignored everything to the right of 100. So you've just ignored half the tree, and that's why you get log n again. Now 70 is greater than 30, so you're going to go to the right of 30, follow that reference. You will go to the node that has 30 and 35, you're looking for 70, so you will follow the what's called the sibling reference to go to the node that has the 100, 101, and 110, and since the first entry is 100, then 70 does not exist, and you return an empty result set to the user without at all going to the table. You've figured out that the value 70 does not exist in the table because the values that were in the column that you used to create this index, this B+3 index, does not have a 70. Okay? Now the actual column that existed in the table that you have read and created this index from, we haven't discussed how we actually create the index, but that actual column is all the leaves at the bottom layer. If you sort the entries in that column, it's going to be 3, 5, 11, 30, 35, 100, 101, 110, 120, 130, all the way to 200. This is the content of that column. You've extracted the content when the user typed create index, on this column, say H, no, not H, because you have here 156, 179. I don't think anyone reaches that age. Let's say this is the amount of money someone has in the bank or customers has in the bank, whatever. Okay, so you've extracted those values that appear at the leaf level and you create this index from. So you could actually find out if a value exists or not without going to the table, by just searching for it in the index. Now the next thing I'm going to introduce is this n value that appears at the top right. This is a very important parameter of B+3s. It tells you the maximum number of keys you could have in a node. So this is not the minimum, this is the maximum. If I say n is equal to 3, then at most I could have 3 keys in the node, which consequently means 4 references. as we said, it's n and n plus 1. If n is equal to 20, that means I could have a maximum of 20 keys in the node. So notice here n could get big, and actually it will turn out to be quite big. And this is something very interesting about B+3s, that the number of keys each node will hold as a maximum could be quite big. In fact, as you will see, it's going to be typically 256. So it's going to be quite a big number. Okay? So let's move on. This is what I already described before, that we have a relation between keys and pointers. It's always n keys and n plus 1 pointers. Okay? Regardless of what n is, it's always going to be n keys and n plus 1 pointers. Even if we have n equal to 1, that's going to be 2 pointers. If n is equal to 1, that's actually a binary search tree case, okay? Where you have one value stored in the node and you have 2 references, left and right. Okay? So this is a relation that will always hold, as you will see. Now we come to the important feature of B+3s, which is this notion of the tree always balancing itself. The way the B+3 enforces self-balancing is by setting a minimum number on the pointers and consequently keys that could exist in each of the leaves and the non-leaves. You see, the rationale goes like this. To get a skewed tree, then that means you started with a tree that was quite simple, perhaps of 1 or 2 nodes. And we can't describe a tree that has 2 nodes being skewed. And you kept adding nodes to one side and leaving the other side empty. So to avoid, having this kind of behavior, which is filling one side and keeping the other side empty to get skewness, we will set a minimum on what a node can have. And consequently, we cannot go below that minimum. And consequently, we will not have this notion of emptiness where there is an empty part in the tree, because every node has a minimum that must be respected, and we got to do something about it so that it's always, at the minimum or above the minimum, but it's not below the minimum. Okay? So in the case of B+3s, and by the way, this is a very popular idea in self-balancing trees, setting a minimum on things. Okay, so you don't have this notion of filling one side and keeping the other empty. Now, the way it's done in B+3s is we're going to set this rule. We're going to say that the minimum for the non-leaf level is going to be n, which is the number of keys, plus 1 divided by 2, sealed up. The minimum at the leaf level is going to be n plus 1 divided by 2, floored. Now, I will show you some examples with numbers, but let's just look at this and try to figure out what is this going after. If I say n plus 1 divided by 2, it's almost like saying n by 2. It's almost like saying that I want to keep the minimum as half. So if I set my n equal to 10, the half is going to be 5. Because I'm dividing by 2. And it's going to be 5 at the non-leaf level, and also something close to 5 at the leaf level. So basically I am saying I will have at least half my n, which is the number of keys, as a minimum. I cannot go below that, because once I go below that, I will start having to have skewness. Now, why the flooring and the sealing here? You see, when we are at the non-leaf level, we would like to increase the number of pointers, because this gives us more branching. So what we're going to do is we are going to floor up to have more pointers. Okay? And that's why, sorry, we're going to seal up, not floor up, we're going to seal up. That's why we're doing sealing in the non-leaf, to have more pointers. But when we are at the leaf level, we don't want that, because there's no notion of branching at the leaf level, okay? Because the leaf does not have any branches below it. It's the last level. a leaf by definition has no children, so there's no branching there. Okay, and this is why we're doing their sealing versus flooring. We're interested in introducing branching in the B+3 by demanding more pointers, basically, and we will get that when we seal up. So for n equal to 3, just to stress the idea here, if you have the maximum number of keys in a node 3, let's look at the leaf level first, because it will make more sense to you, since these are the values we got from the column. So if at the leaf level I said n is equal to 3, this is applicable to the leaf and the non-leaf. Okay, so when we talk about the full node, then if n is equal to 3, then n is equal to 3. It means the maximum number of keys I could have is 3. At the leaf level, you will see the 3 values, 3, 5, and 11, okay? And associated, as we said before, with every one of those is a reference to where that row is. That has the value 3, or that has the value 5, or that has the value 11. And then you get this sibling node. This sibling reference that takes you to the neighbor leaf, okay? Now, if you look at the non-leaf level, we already explained this. If you have 3 keys, then you must have 4 references. So here's n and n plus 1 again. Okay? Less than 20, 120, between 120 and 150, between 150 and 180, and greater than 180. Okay? Now, in the case of the non-leaf, the minimum is going to be n plus 1, which is 4, divided by 2. Well, unfortunately here it's a perfect division, so 4 divided by 2, so the number of pointers is going to be 2. Okay? When n is actually even, it will make more sense to do the sealing, and as you will see there, you will get more pointers. And that's why we always prefer n to be an even number, so that when you seal, you get more pointers. Now, but again, let's look at it here with n equal being odd. So I'm going to add 1, becomes 4 divided by 2. Sealed up, it's still 2. So I'm having 2 pointers at a minimum. If I have 2 pointers at a minimum, then I must have 1 value, because it's n and n plus 1. If the pointers are 2, then the key has to be 1. And this is the example here where, it's the 30 alone, and I have a left reference and a right reference. Okay? Now, in the case of the leaf level, we said it's going to be again n plus 1, which is going to be 4 divided by 2, and then floored down. So again, the effect here of flooring and sealing is ignored, because we don't actually affect the result, because the output is going to be 2 anyway. So I have 2 pointers, and at the leaf level we said with every pointer we associate a key. So if I have 2 pointers, I will have 2 keys. Okay? And you might tell me, about what about the rule n and n plus 1? Well, the sibling reference will count. So it's still n being here, or 2 keys, 30 and 35, and 3 references. Reference to where the row 30 exists, the reference where the row whose value 35 exists, and the sibling reference to the next node. So we are still respecting the rule n and n plus 1. So let's try to consolidate our rules here in one picture. So maximum number of keys per any node, whether it's a root, the leaf, or non-leaf, is the same. It's going to be n. Maximum number of pointers associated with any node is also going to be n plus 1. So this is fixed for all the 3 types of nodes we would have: the root, the leaf, and the non-leaf. Now, the minimum number of pointers to the leaf and the non-leaf we've already discussed. It's for the non-leaf n plus 1 divided by 2 sealed up, and for the leaf is going to be n plus 1 divided by 2 floored down. the minimum keys consequently is going to be related to the minimum pointers, because if I say that the minimum pointers is n plus 1 for the non-leaf is n plus 1 divided by 2 sealed up, then the keys is going to be n plus 1 divided by 2 sealed up minus 1, because you gotta get 5 keys and 6 pointers, or 7 keys and 8 pointers. So always the number of pointers is plus 1 the number of keys, or in other words, the number of keys is the number of pointers minus 1. Now for the case of the leaf, the number of keys is going to be the same as the number of pointers if we exclude the sibling reference that we discussed already. Now the root is a special case. We will accept, regardless of the n, that the minimum number of pointers and keys at the root level will be 1 for any n, whether it's n is equal to 256 or n is equal to 128 or n is equal to 10 or n is equal to 50. The root minimum keys and pointers is going to be 1 and 1. This enables us to construct the tree in the first place, because when we have one key, which means that the table has one row, and we retrieve that row and we got the value in the column we're building the index on, we will end up with one node which has one key and one reference, which is a reference to that row, and consequently the minimum has to be always 1 and 1. So I already mentioned before that n in the B plus tree is actually quite big. How big is it? It's actually related to the cylinder size, the topic we discussed before in lecture 1. So in most hard disks nowadays, the cylinder size, as if you recall, varies from 16 kilobyte all the way to 64 kilobyte. So the question becomes, how many keys and references we can squeeze in one cylinder? So if the cylinder is 16 kilobyte, the question becomes, how many keys and references can we squeeze in 16 kilobyte? If the key is an integer, it's gonna take 4 bytes, and if the reference is an extended reference, it's going to be 8 bytes. If it's a regular reference, it's going to be 4 bytes. So now what that means is, to have a key and a reference, if you just count it as 4 and 4 for the key, 4 for the reference, that's 8 bytes. Now you divide 16 kilobytes by 8 to know how many you can put in a single node. Okay? How many keys and references you can put in a single node. So if you substitute with the same table we were looking at, with n equal to 256, and in your textbook actually they go into the same description as I'm mentioning here, with actually the numbers, so you can get a sense of how this is computed. So if n is equal to 256, then maximum keys is 256, minimum pointers is, the non-leaf is 129, and the leaf is 128. This is the branching I was referred to, which is the effect of the sealing up. That's why we got 129 instead of 128, because we sealed it up. And this is what we want. We want to have more branches. That's why we ended up with 129 instead of 128. Now, if you look at this, and I'm telling you, this is actually the typical size of an n, which is 256. Okay, so you have at most 256 keys in a node. That's a lot. That's actually a lot, because in that node, you will have at minimum 128 keys in the non-leaf level and 129 references, or 129 children for that node. So you can imagine how much branching we're doing here. So when you actually go through this node and pick one of the branches out of the 129, you are ignoring the 128 references and just picking and following one specific one of them out of the 129, and that means you're reducing your search space super fast. It's incredibly fast. So you could basically go through a list of hundreds of millions of keys, or basically a B+3 of hundreds of millions of keys, because the table had hundreds of millions of rows. And you can actually go very quickly traversing this tree, narrowing down your search space super fast, because you have like 129 branches at every level, and you pick one and ignore the other 128 with all the data underneath them. Okay, so it's quite impressive, you know, if you think of it. The fifth thing we're going to learn about B+3s is that the magic happens in the insertion and deletion. These two operations guarantee all the time that the tree is balanced. So while the search actually does not affect the structure of the tree, the insertion and deletion do change how the tree look like to make it a little bit more balanced, or to, in other words, to preserve the minimum number of keys we have set that we need to respect all the time. So let's start to see examples of insertion and deletion. We will look first at insertion. Okay, we have 4 cases, from the simple one to the a little bit surprising one, which is the new root. Okay, let's actually you know, see every case separately and discuss how it's actually executed. So assume we're giving the following B+3. I'm not showing the whole tree here because I don't have space in the slide, so I'm just showing you the part where the change will happen. I'm showing you the left part, but this is definitely not, if this is a B+3, a properly constructed B+3, this is not a skewed tree. You know, there is a right side here that doesn't show up just because of, you know, I didn't bother to put it in. Now, let's say you have this B+3. The information you need to learn is what's your n, and n here is set to be 3, which means at most you could have 3 keys per node. Applying our formulas that we discussed earlier, we find that if n is equal to 3, then the key count, not the reference count, the key count, the formulas you've seen before were actually for the reference count, which is key plus 1. But I'm just using here the key count as my guide, which appears at the bottom right of the screen. So for the non-leaf level, again, the maximum is 3, this is n, it's not changeable, and the minimum is 1. Okay? At the leaf level, the maximum is 3 and the minimum is 2. If we apply the formula we have seen before, which gets you the number of references, not the number of keys, it's going to be the minimum is 2 and 2. But at the leaf level, you know, we have 1 key associated with it as a reference. So that's why I'm saying here I have 2 keys at the leaf level, while I have 1 key at the non-leaf level. Okay? And I will still get 2 references, because the references at the non-leaf level is going to be less than and greater than. Now, let's say you would like to insert 32. So you start at the root. You always do that with any tree. You start at the root. 32 is less than 100, so it's going to be placed to the left of the 100, so you follow the left reference. 32 is greater than 30, so you follow the right reference, the right of 30. And finally, you come to the node that has 30 and 31, and this is actually a lucky scenario because we have a space available for us to insert the 32, and that's what we do. We're going to put the 32 there. And here it is. We will insert it along with the reference that we got for the row that has this 32 value. So this is obviously a no-brainer. There's really no change to the tree. Everything is working to our advantage because we had a space and we didn't cross the maximum. Okay, because obviously in the insertion you will always be bothered about, am I going to exceed the maximum? And here the maximum is 3, so I cannot have 4. Okay, but here we had 2, so when we add 1 it's 3, so now it's fine. Let's look at another example, you know, where we start to see things a little bit, you know, performed in a little bit different way. So here I'm going to insert 7 for the same tree we looked at before with the same n equal to 3. 7 is less than 100, I move left to the node that has this 30. 7 is less than 30, I move left of 30 to a node that has 3, 5, and 11. Now here is the problem. This node is full. N is equal to 3. The maximum number of keys I could have in a node is 3, and I'm already at that maximum. And these maximums and minimums are enforced to make sure that the tree is always balanced. So I need to do something. I need to insert the 7 here. So I need to do something to be able to insert the 7. Okay? So what I'm going to do is I'm going to follow my sibling reference to the next node, which is the one that has 30 and 31. And I will go there to check if there is a space, because the proper location for 7, the one that I must, use, is after the 5, the location of the 11, what is currently occupied by the 11. So I'm having trouble with this 11. So I would like to move it so that I could put the 7 there. So what I'm going to do is I am going to actually check the adjacent node to the right, because since the 11 is the rightmost key in the node, I'm going to check the one after it, which is, so I'm going to follow the sibling reference to the one that has 30 and 31, and I'm happy because actually there are only 2 keys, so I can move the 11 there. Now, when I move the 11 there, now I've emptied the space for the 7, I'm going to insert the 7. But I have to remember there are other invariants associated with the b+3. There is an invariant that says that everything to the right has to be greater than or equal to the value. So everything to the right of 30 has to be greater than or equal to 30. But I've just moved 11 there in that node. So obviously 30 cannot stand there as a value because it's not correct. So what I'm going to do is I'm going to put the 11 instead of the 30 to have this invariant hold. Okay? Now, what I just described is one way to do it. And this is obviously the common sense way. But here is the thing. I always like to start with that scenario because this is not what we're going to do. We're going to do something else. So I'm always like to introduce it this way so you remember what to do. Okay? What I'm going to do is something else. So again, what I just described in the previous slide is incorrect. I always like to trap students with this explanation because that's what you always think of in the first attempt. I'm going to tell you shortly why this is really not the right approach. But here is actually what I'm going to do. I had 3, 5, and 11. So what I'm going to do is I'm going to create a new node, and I'm going to move the 3 and 5 there, and then put the 7 with the 11. You see the description, the explanation of slide 18, the previous one that I'm referring to now as, even though it will work, this is not what we're going to do. That explanation is valid. And what I'm describing here also is valid. It's valid in the sense that it will give you a proper b+3. You're not violating any of the invariants. But here is the issue. We're not going to do that again. So what I described in slide 18, don't do it. And usually I would get a quiz or a question in a quiz or in a midterm or an exam, and students will still insist on doing it. Okay, so don't do it. That's why I started with that. Don't do it. Do something else. What are you going to do? Here is what you're going to do. In insertion, as a rule, we will always favor creating new nodes. Let me repeat that. In insertion, as a rule, always remember this. We will always try to create new nodes first. Why? Because when we create a new node, and if you really think of how big the n usually is, which is like 256 or 128, when you create a new node, that will actually give you an opportunity to do way more inserts in the future without actually creating any new node. Okay? So you're opening an opportunity, or you're opening the space for further inserts that will cost you nothing, because there will be a space for them. Because when you create a new node and you're respecting the minimum, if your maximum is 256, your minimum is 128, and when you favor creating a new node that has 128 keys, you have another 128 keys you can insert without creating one more new node. So the rule is favor creating new nodes. So going back to our example, we started with trying to insert 7, and we reached the node that had 3, 5, and 11. I could have moved the 11 to the right side and inserted the 7 there, but this does not favor creating new nodes. So what I'm going to do is I'm going to favor again creating new nodes, which means I will create a new node when I find the node is full I'm trying to insert there, and I will move to the new node whatever I'm supposed to move, whatever I should move to enable my insertion. And in this case I have to move the 3 and the 5. to enable the insertion of 7 beside the 11. Okay, so rule number 1 in insertion, always remember, favor creating new nodes over using what you have. Now, rule number 2, which is very much attached to rule number 1, whenever you create a new node, you have to point to it from the above level. And that means you're going to add a new reference to the level above it. And you cannot add a reference without adding a key, because you have to respect the relation between the keys and the references. So again, rule number 1, favor creating new nodes. Rule number 2, point to the new node from the above level. Rule number 3, make sure that you increase the number of keys as well, because you cannot add a reference without adding a key. And that's exactly what you see here. I'm going to add the reference and add a key. Now the question is, which key? We have to remember the B plus 3 invariant, which is the same as the binary search tree invariant. Any value that appears to the right has to be greater than or equal to that value. Okay? So what this means, I should go to the right arrow of the new value I'm trying to insert, which is the 7 in red here, in the second level in the B plus 3. Go right and find the smallest value there. And the smallest value is going to be the first one to the left, which is the 7. So I put it as the parent. Okay? This will be the new key I introduced in the parent level. So again, 3 rules associated with insertion. Favor creating new nodes. When you create a new node, you have to add a reference to the above level. When you add a reference to above level, you have to add the key to the above level. Where do you get the key from? Go to the right and then all the way to the left. Again, go to the right, all the way to the left, get the smallest value in the right subtree, which is going to be the 7. Let's look at this example. Here I would like to insert 160. Again, my n is 3. 160 is greater than 100, I move to the right. 160 will reside between 150 and 180, so I follow the reference that is to the right of the 150. And there I have an issue as well. The node that is to the right, that the right reference of 150 is pointing to, is full. It has 150, 156, 179. 160 will go in between 156 and 179, but I cannot put it there because I'm already at my maximum. So what I'm going to do again is favor creating new nodes. Now when I favor creating new nodes, I have to respect the minimum. So at the leaf level, the minimum is 2. So I will take the 160 and 179 and create the new node with those 2 entries. Now the second rule we said associated with insertion is, when you create a new node, point to it from the parent. So I go to the parent, and now I have a surprise. The parent is already full. The node I'm referring to is the one that has 120, 150, 180. It's already full. It has 3 keys, which is the maximum, and 4 references. So I cannot add any more references, and consequently I cannot add any more keys. So again, when we are actually faced with a situation where we'd like to insert in a node and it is full, then we favor creating new nodes. So I'm going to create a new node at the above level. And that's what you see. I created a new node at the above level, and to find out the value that will go in this new node that is highlighted in green, I go right all the way left to find the smallest value in the right subtree, which is 180, so I put it there. But hey, okay, why is 180 alone? Because remember, at the non-leaf level, the minimum is 1, not 2. Okay? It's 2 references, consequently it's 1 key. So I'm going to apply this same way of thinking again, because I just created a new node, the 180 node that is highlighted in green. I'm going to apply the same logic or the same rule I have described before. So I create a new node, I have to point to it from the parent. Now where is the parent there? It's going to be the one that has the 100. I cannot just plug in a new node and not point to it from the parent level, because this means when I traverse from the root, I'm not going to find it, because there is no one is pointing to it. So when I created the new node, this green node, I have to point to it from the above level. So when I add a reference to the above level, I also need to add a key, because it's going to make the keys now 2 and the reference is 3. The question is, what value again should I put in at the root level? Now, the reference I'm going to add will be to the right of the new value that will go in at the root level. And again, we're going to apply the same rule. Go right all the way left to find the smallest value in the right subtree. So the smallest value in the right subtree is actually 160, and consequently I add 160 to the root. And now here is the full picture, adding 160 to the root. Now again, remember, 160 here is the smallest value in the right subtree. That's why I actually grabbed it all the way from the bottom and put it at the root level. And if you try to check the b plus 3 invariant regarding the greater than or equal and the smaller than, everything is actually now set up properly. Now let's look at this last example. Now in this last example, I'm going to insert 45. So 45 goes to the right of 30. I will go in there, and I got this full node that has 30, 32, and 40. So again, I favor creating a new node, and that means I'm going to take the 40 along with the 45 because my minimum at the leaf level is 2 keys. So I got to take the 40 with me, and now I'm going to try to point to the 40 and 45 node from the parent level and add a reference and add a key. And now, actually, oops, I'm running into this scenario where the parent level is actually the root and it is full. So I have to create a new node to be able to point to this 40 and 45. And the only way I can do that is by making a new root, because I cannot have two nodes being the root for the tree. So first, let's do it step by step. I added the 40 and 45 in the red node, and now I'm going to make a parent to this guy to point to it. Now again, I hope it's clear what value will go in that new green node. It's going to be 40, the smallest value in the right subtree. The left of that, because if I have one key, then I must have two references. The left of the 40 will point to the node that has 30 and 32, which means I'm going to delete the reference that's coming from the old root where I had 30 and a reference that points to 30, 32, and 40. But now I have a problem. I have two roots now. So this doesn't work. So I'm going to create a new root. And this is my new root now. The new root will point to the node that has 10 and 20, and it will point to the 40 node, and the one in green. And what value will go in the new root? It's the smallest value in the right subtree. So you go right all the way left, you'll find 30, you put it up there. Now there is something really interesting about B plus trees. If you've noticed, because we are always favoring creating new nodes, and that will always happen at the leaf level because all the nodes at the leaf level are at the same level, so all of them are are growing basically to the side. No one is growing downward, they are growing to the side, all the leaf level nodes. Because when we favor creating a new node, it's going to be at the same level as the other leaf levels. So the tree is growing horizontally first by expanding the leaf level to the right and to the left. And then from time to time, we will expand the level above it. And even less often, we will expand the level above that, until we create a new root at some time in the future. And that's what you see here with this example. Okay, so the tree is growing horizontally and then upward horizontally all the way till suddenly you start seeing a new root up above the level you had as a root. Okay, and this is really a property of how things work, or an output of how things are executed in a B plus tree. Okay. Next, let's look at deletion in a B plus tree. And you will see that deletion is actually the complement of insertion in terms of its policies and how it approaches removing an element from the B plus tree. So again, we have 4 cases, starting from the very simple case to the more sophisticated case. Let's look at them one by one. So the first case is trivial, which is I delete from a node and I don't change anything in the tree. So I'm not going to cover that. It's common sense a situation where if I go to a node and I'm deleting an entry and I didn't go below my minimum, because what we will worry about here is going below the minimum. If I don't go below the minimum, then I'm just going to delete it. So it's again like the simple case in the insertion, in case number A in the insertion. So let's move on to the more serious or involved cases, I would say. Now let's look at this b plus 3, and here I change the n to make the n even, and the n is set to 4, which again, applying our formulas to calculate the number of references and consequently the number of keys. If n is equal to 4, I would have as a minimum 2 keys in the non-leaf level and 2 keys in the leaf level. Consequently, I will have 3 references as a minimum in the non-leaf level, and again you could say we have 3 references in the leaf level. 2 will be for the keys and 1 the sibling reference that takes you to the next node at the same level, at the same leaf level. So let's look at this b plus 3. Again, I'm not showing the whole tree, I'm just showing the part I'm going to work on. I would like to delete 50. I'm going to follow the same approach, which is, look for the value to be able to delete it. So if 50 exists, it's going to be between 40 and 100. I will follow the reference between them, coming to the node that has the 40 and the 50. Now, my goal is to delete 50, but I have a minimum number of keys that I must respect, and the minimum is 2. So I can just remove the 50 and leave the 40 alone. I will indeed need to delete the 50 because this is what I'm after, this is my goal, but then I have to fix the situation of the 40. I can't leave the 40 alone. So I really have here 2 options. Either to borrow the 30 from the neighboring node, or and add the 30 to the 40, so the minimum is 2, the minimum keys is 2, or I take the 40 and move it to the neighboring node, neighboring leaf level, the one that has the 10, 20, and 30. And the opposite of what we consider in insertion is now going to be done in deletion. In insertion, we favor creating new nodes. In deletion, we favor compacting the tree, which means we favor deleting nodes. So if I take the 30 and put it beside the 40, I'm not going to delete any node, to solve my problem, to have minimum of 2 keys. But what I'm going to do instead, I'm going to take the 40 and put it along with the 10, 20, and 30, because I'm trying to get rid of nodes here. Instead of trying to create new nodes, I'm trying to get rid of the node. So when I delete here a node, generally in the deletion, when we delete a node, we have to erase or remove or delete the pointer pointing to it, the reference pointing to it. And if we delete the reference pointing to it, then we have to also delete the value that is beside this reference. Again, this is exactly the opposite of what we described with the insertion. So here is the picture. I'm going to delete the node, delete the reference, and delete the 40 because it was taking me to this node that I'm deleting now. And I will move the 40 that existed in the node where it had 40 and 50. I will move it to the neighboring node. Okay, so again, this is showing the approach here. Insertion made the tree grow horizontally, and after a while it will grow vertically up. And what we're trying to do here is do the opposite by shrinking the tree horizontally by removing nodes, as if we can do that. Let's look at another example. Here I'm asked to delete the 50. So again, if 50 exists, is between 40 and 100. I go there and I got 40 and 50. And now again, I have to respect the minimum. It's the same story we've seen before. So my first choice is always to try to delete the node. But if I can't, well, okay, I still cannot leave the 40 alone. So I will borrow the 35 from the neighboring node. Why the 35? Because it's the last number in the node, and the numbers, as you notice, are ordered in every node, so it's the last number, and I will move it beside the 40. And when we redistribute keys like this, we have to fix the parent. So if I move the 35 right node to be 35 and 40, I have to change in the parent level the value that was taking me there. It's now going to be 35 because it's going to be the smallest value in the right subtree. So everything to the right of this value is greater than or equal to it. Let's look at the last case where we're going to see something that is exactly the opposite of what we have seen before. In this case, we're going to actually reduce the height of the 3 by 1. So let's start. Again, I'm trying to delete 37. If 37 exists to the right of 25, I come to the node that says 30 and 40. If 37 exists, it's going to be between them, so I follow the reference in the middle between 30 and 40, and I go to the node that has 30 and 37. My goal is to delete 37. I will remove 37. Now I'm stuck because I got this 30 in a node and I need to have the minimum of 2 keys. So again, the strategy here, favoring compaction, favoring deleting nodes. So I will delete the 30 and I will move it from this node, and I will move it to, or basically I'm deleting this node, I'm moving the 30 to the left node. Okay. Now, why did I do that? Because I have a space. Now again, deleting a node means also deleting a reference pointing to the node, means also deleting the value associated with that reference, which is the 30 that exists in the second level, and I've crossed it with a red mark. Now, here is an issue. Deleting the 30 in the second level will leave the 40 alone. And the problem is, according to our invariant, we should have a minimum of 2, not 1, in the non-leaf level. So I can't leave the 40 alone. So again, we are going to favor deleting nodes here. So I'm going to delete the node that has the 40, and I'm going to move the 40 to the sibling of this node, which is the one that has the 10 and the 20. But now I have an issue. 40 has 2 references, less than 40, which is pointing to 25, 26, and 30, and greater than 40, which is pointing to 40 and 45. The sibling to it, which is the 10 and 20, already has 3 references. So if I move the 40 to this sibling, I will have 3 values and 5 references, or 3 keys, 10, 20, and 40, and 5 references. And that's not acceptable because our rule is n and n plus 1. N keys and n plus 1 references. And really the issue here is that it's not just that I have n and n plus 2 references, n keys and n plus 2 references. There will be a node that has no associated value. That is the node that has 25, 26, and 30. So what I'm going to do to fix this scenario is, to fix this problem, I'm going to squash the root into this sibling. So this is the first step I was referring to, and this is the squashing of the root. To be able to have 4 keys and 5 references. Notice what's happened here is that the tree, according to our way of working here, is shrinking horizontally, and this shrinking is propagated from time to time when we go below the minimum in the non-leaf level. So we do the shrinking at higher levels as well. And from time to time as well, we are going to end up squashing the root into the lower level. And consequently, the tree will shrink the same way it grew. It grows horizontally, and then ultimately the root goes up 1 level in the insertion, and because of the deletion, it will be compacted horizontally, and ultimately the root will go down 1 level instead of going up 1 level. So it will go down 1 level, okay? So again, that's why I said that deletion is the complement of insertion in the B+3 way of working. Next, I would like to discuss with you when should we use a B+3. As I mentioned earlier, we have many types of indices in the database world, and any decent database engine would come with at least a dozen of indices. And one of your roles as a computer scientist is to figure out which index to use based on the SQL statements you're running. So you would typically create a B+3 if you want to support queries on exact value. What is a query on an exact value? Like select star from where x equal to 20. So that's an exact value, 20. Or where name equal to Ahmed, that's an exact value, okay? Or where, temperature equal to some number. So that's an exact value query, okay? And also, you want to support queries involving a range search. Why a range search? Now, example of a range search is like saying select star from where x greater than 10 and x less than 50. So you're looking for values between 10 and 50. Why, again, is range searches supported nicely using B+3? Now, remember the siblings pointer at the leaf level. This pointer that takes you to the next node at the leaf level, your adjacent, the node adjacent to you at the leaf level, is really good in actually answering range queries. Because if you have a query select star from x where x greater than, or select star from this table where x greater than 10 and x less than 50, what you do is you go and search for 10. As if you're looking, as if you got the query select star from this table where x equal to 10. So you do a search starting from the root for 10. And when you find the 10, you move horizontally in the table, in the index at the leaf level, visiting the nodes at the leaf level one after the other, following the siblings pointer until you stop at the 50. So going from the root all the way till the 10 is going to be log n because of the nice divisions, because we are having a balanced tree. B+3s again are balanced trees, so it's going to be a log n performance. And reaching to the 10 is in log n, and then you do some key processing to actually collect the entries that you're interested in, which is between 10 and 50. So what I'm telling you is, if you have exact value queries, like select star from this table where x equal to something, or select star from this table where x is between this and that, then for sure B+3 will help you in both cases and will give you log n in both cases. Nice thing as well is that if you would like to support aggregate functions, if in your SQL statement you have things like, select star from sum of x or average of x and so on. Why? Because remember, at the leaf level, what you are seeing is the content of the column you are building the index on. So you don't have to load the table. Maybe the table is too big to load from disk, but working with the index will get you all the values you're trying to apply the aggregate function on. So just retrieve those values from the B+3 leaf level. So if you would like to support the three of them, if you have those three types of queries, or a query that has a mix of those three features, then for sure B+3 will be a great tool as an index to use, and you will get the nice log n running those queries. Without a B+3, without index, or without an index in general, you're going to go for an O of n performance, and we said this is not acceptable, especially with the volume of data we would be typically working with in a database. So here's the 10th takeaway for you in this course. A B+3 index should be used when you want to enhance the performance of SQL queries on exact value, SQL queries with a range search, and SQL queries containing aggregate functions. How do you actually create a B+3? Because I've already told you there are many indices types in databases. Any decent database like Oracle or SQL Server or Sybase or Postgres or MySQL will have a number of indexing data structure. So if you'd like to force the database engine to use a specific data structure like a B+3, then you have to specify that somehow. And I already mentioned that last time when we were explaining when I was explaining, I don't like to use we about myself, so when I was explaining the Brin index, that in Postgres, the way you do it is you use the keyword using, and then you specify the name of the index type. So in Postgres you would say using B_3. Now this is again Postgres flavor of doing it. This is Postgres way of doing it. Microsoft would do it differently in SQL Server. Why? Because again, I think I mentioned that last time, it's not part of the SQL standard to specify the index type. So every database engine would do it in a slightly different syntax. Okay? And I definitely invite you to go and read the documentation about the B+3 in SQL, in Postgres. I've linked it here for you. You would pretty much see what we have been describing. Everything that we described here is stated in that page, but with some additional details that is specific to Postgres implementation of B+3s. Now, I would like to conclude today's lecture with an important clarification about a topic that often confuses students, which is the difference between an index, a key, and the notion of clustering. Okay, the confusion generally is coming from you getting exposed to this concept in database 1 or your first database course without learning about the index and without learning about the importance of sorting the data in the pages according to some column. So the concepts that you learn from database 1 sometimes causes confusion when we add more details like what we are doing here in this course by describing indices and sorting mechanisms and so on. So I would like to clarify that. So the first thing I'm going to say is that the concept of a key that enable you to distinguish between rows, it's a logical concept. It's coming from actually relational algebra, okay? You need to differentiate between the concept of the key and the concept of an index, and I think by now you understand that an index it's just a secondary storage data structure. It's not the relation, it's not the table, okay? But let's try to mix these things together with the notion of clustering. The word clustering means really here ordering or sorting. It's not called ordering or sorting in the database world, it's called clustering. It's more fancy name. It's an older name actually. It was invented in the database world and they still are stuck with it, okay? So when we refer to clustering, I'm referring to how the data is stored in the file, or in other words, how the data is sorted in the pages of the table. Okay, we said that we're going to divide the table to pages and we are going to sort according to some column, and we said if we build an index on that column, it's going to be called the primary index. The notion of sorting from now on, we're going to call it clustering. Okay? So we could talk about, instead of saying the column I'm sorting the pages of the table according to, I'm just going to call it the clustering column, which is the column used to sort the table. Okay? So now we have the clustering column. Okay? So a clustered index is an index built on the clustering column. Does this sound familiar? Yes, this is the primary index we discussed before. But the word primary index historically was introduced many years back in the context of what I described in lecture 1. Okay? So if you didn't see lecture 1, go back to lecture 1 and understand what is a primary index. Okay? Another more modern name for it, but it is not referring really to a primary index as much as it's a clustering index. So I could create a B+3 to be the clustering index. What does that mean? It means this B+3 is created on the column used in clustering, which means it's the column used in sorting the data. So if you read this, it's the clustering B+3 or the clustering BRIN. That means, or a clustered BRIN or a clustered B+3. That means it's an index built on the column used to sort the pages of the table. Okay? Now, there's one thing here. Remember when we discussed primary indices, we said that primary indices, comparing them to secondary indices, will always be a little bit more efficient in one aspect, which is that with secondary indices, which are indices created on columns not used to sort the data, which means they are non-clustering indices, we will have to create a first level that is dense, that has all the values of the column we're building an index on, but sorted. Because in the table it is not sorted according to that column, so we're going to sort it outside and then build the index on it. Okay? So generally, clustered indices are thought to be a little bit faster than non-clustered indices. Because with clustered indices, you have already the values sorted in the table in that column you're building the index on. You don't have to extract the values and create a first level dense index out of the values that is sorted, so that you can later on create the other indices you are after, or you know, put other levels behind that, as we discussed in lecture 1. Okay? So clustered indices are generally considered faster. Okay? But notice in all of my discussion, I didn't refer to keys at all. Okay? I didn't refer to the concept of a key. What does that mean? It means I could cluster according to anything. And this is probably the new thing that students discover when we discuss this, is that you don't have to cluster according to the key. You don't have to sort the rows in the table according to your primary key. You could sort it any way you like. The primary key is something else. Okay? So this is again to stress the point. A non-clustered index, it means it's an index regardless of the index type, whether it's a B+3 or a hash, which we're going to see later on, or a Brin index. As long as it's made on a column that is not used to sort the data, it will be called a non-clustered index. Okay? Now, obviously, you will always have one clustered index, regardless of the specific index data structure you're using, and all the other indices on all the other columns are going to be non-clustered. Okay? And this is what we have previously called secondary indices. But secondary indices are if you'd like, is this very special case of non-clustered index, and it is what we described last time, the way the index is built. Okay? A little bit of a naive approach, because we said that approach for primary and secondary indices creates us a trouble. It will speed up the search, we'll get the search and log n, but the insertion and deletion will be, you know, really bad because of the need to shift things, to shift the rows, okay, or to do fragmentation of the rows. So I hope now it is clear for you that, you know, what do we mean when we say clustered index? It's some data structure, some index type that is built on a column that is used to sort the data on the disk, okay, in the pages of the table. Non-clustered is something else, as we already described. Now, how do you specify how you sort the data? So I'm showing you here the syntax for SQL Server, the one you use in Database 1. Okay? Look what is happening here. I'm saying create table, some table, and I specify the columns. ID, it's an integer, not null, primary key. This is the primary key, the ID column. And then I put beside it the keyword non-clustered. So I'm telling SQL Server, don't sort the content of the pages of this table that's called a table according to the ID, because the default is to sort according to the primary key. But you can change that behavior and by just including the word non-clustered. Now then the question is, according to which column the data will be sorted? Well, here I'm sorting according to postal code. I could sort according to anything basically, okay? So now an index created on postal code is going to be a clustered index. And an index created on ID, even though it's the primary key, is going to be a non-clustered index. Okay? So you could sort according to any column you like. And consequently, that introduces obviously confusion when the students learn about this for the first time, because the assumption is that the data will be sorted according to the primary key, and actually there's nothing in the relational algebra that you've learned in Database 1 that sets a constraints according to, sets a constraint that will force us to do this. Okay? A primary key, that is not null is some value that distinguishes the row. Whether the rows are sorted according to that or not, that's another question. Okay? So don't confuse the notion of primary key with clustering with indices. So here's the takeaway. The clustering or sorting column does not have to be the key column. Any column could be used in clustering the data in the pages of the table. This is the material for today's lecture. I'm putting for you the content and the pages you have to read if you have any issues, and The link that I was referring to for the Postgres is available in the slides, and this is another one for the Wikipedia entry for B+3s. So again, go ahead and read them to consolidate what you have learned in today's lecture.